Google, Amazon, and IBM are spending tens of billions on it. Researchers think it could revolutionize science and medicine. So, what is it? Quantum technology, but it won't just change computing and research. It will also shape the networks of the future. I'm Diana Goovertz, and this is the 5-9. You've probably heard about quantum computing or quantum networking in news headlines, but just so we're all on the same page, here's a quick breakdown. Quantum computing and quantum networking are two branches of the same field. They both use something called qubits or quantum bits as their basic unit of information. And quantum computing typically requires a lot more qubits than quantum networking to function. There are live deployments of both quantum computers and quantum networks in the wild today, but both still have a ways to go before they fully mature. So, in this episode, we are zooming in on quantum networking, taking a look at the current state of the field, use cases, what it'll take to reach quantum's so called ChatGPT moment, and how the technology could change the shape of the internet. With us today, we have two leaders in the field, including Noel Goddard, who is CEO of Qunnect, and Frank de Jong, who is Quantum Safe Network Lead at Orange Business. My colleague Masha Abarinova has been covering this pretty regularly for Fierce Network, so I will leave it to her to grill our guests. Masha, take it away.
Thanks, Diana. Noel and Frank, thrilled to be having this chat with you both. Why don't we start with the basics? What's the current state of development in the quantum networking world?
So I think we're all familiar with the extraordinary advancements that the digital internet brought to our current level of digital computing. And that's not just because the computers themselves are networked, but it's because the internet, as we think about it, connects all sorts of things like IoT devices and grids and other things. So the promise of what quantum networking will bring is a similar type of vision, where basically quantum devices, whether they be quantum computers, but all of the other types of devices which are starting to come to market, will be connected and networked by this larger quantum internet that will empower the applications of the future. So these networks distribute a new type of information. So this, we call it entanglement, which is a special type of quantum information that's carried by particles of light that are entangled by the nature of how they were created. And while that sounds very sci-fi, actually, these networks have been deployed today. Qunnect's hardware supports networks which have been deployed in the New York City region, Berlin, Montana, and now soon to be also Albuquerque in the US. All of these are supported by a network infrastructure that looks very much like the server racks that you have in a normal digital network. They're just there to support the quantum networks and quantum information being pushed through what is the existing fiber infrastructure. Governments and enterprise customers are both supporting this today. So you're seeing investments in Asia, the EU, the US, and by enterprise customers in all of those regions as well, knowing that the next step in information technology, so we all have been here for the AI revolution, right, will be quantum, and quantum networking will unlock that. Frank?
Yeah, one basically put some extra meat to the bone on that. Well, for us, at Orange Business, we have been working quite a lot with, on the innovation side, together with all kinds of technology vendors, and we got to the point where we say, okay, now all this innovation and all this research and development is all nice, but at some point in time, it needs to get to a point where, as a telco, you can provide services to your customers on this as well. Now, while we believe that the quantum internet is something that is bound to happen in a few years from now, like at the scale where a telco operates. We started to look at specific use cases for this so-called quantum internet. And one of the use cases that we are looking at right now is quantum key distribution. So we're specifically targeting at this point in time customers with let's call it a very high security profile, because due to the nature of quantum key distribution and quantum technology, there is a possibility to, let's call it, provide a guaranteed security on connections like that. Now, that's something that I think every customer would want to have at this point in time, very specifically because there is something with the advent of quantum computers, there is something else coming our way, which I think the whole market calls the quantum threat. If we talk about VPN connections nowadays, they use an algorithm which is relatively easily broken by a quantum computer, assuming you have a quantum computer of a decent amount of qubits, for example. Now, the whole point here is that we believe that in a few years from now, such a quantum computer would be available. So we are now looking at how can we make sure that our customers remain safe against the threat of the future. And that's why we use something called quantum safe networking. And then I think the question was, what's the status of that right now? We have deployed a quantum safe network for us at this point in time in the area of Paris. Orange Business is, our headquarters are in France. So we made a ring around Paris, which we are using to connect our customers at this point in time.
Both of your companies have deployed commercial quantum networks. Frank, can you walk me through the challenges you experienced today in scaling the network and making sure the technology works when it needs to?
Yeah, there are a few challenges at the moment, which we, I think, even together with all of us on the call can overcome at some point in time. But if you look at the way we do this right now, we've built out a few nodes, as we call it. So those are called trusted nodes. But one of the things when you want to do like quantum entanglement or quantum superposition and bring over those qubits from one side to another, there is a limit to the destination that you, also to the distance that you can cross over a normal fiber. And one of the things we at Orange said we want to do, we want to use normal commercial grade fiber. Now, at this point in time, we realized that about 150 kilometers is about the max that we can transfer a qubit from one side to another over normal commercial grade fiber. That means that after 150 kilometers, you need to put some device in the middle, which at this point in time is a trusted node, but it could be a quantum repeater or something like that as well. Now, if you would have to deploy all of those every 150 kilometers, it gets expensive pretty quickly. So that's something that it's still a bit challenging. Now, that will, over time, become easier. I think most of the scientists, probably also Qunnect, is working on that type of technology, but it's not commercially available at the scale that we want to have today yet. So that's one of the challenges, but there's another challenge which is not so technical, and that is if we talk to customers right now, those are the customers that have a very high risk profile. So the financial entities, for example, governments, they also have a pretty well-trained security department. They really want to understand the exact detail of what it is that we are doing. So we spend a lot of time educating them, explaining to them what's happening, why it is important. I think that's the biggest thing right now. And then the third one is very simple. Since the technology is relatively new, it's relatively expensive. And so we need to get to a level where things are less expensive, where more, either becoming smaller, miniaturized, or getting, basically more units built per year, for example. Then we can get to a pricing level that probably will bring it to a bit more customers. And then I think I'll stop here because there's many other challenges, but challenges are here to be overcome, right?
Noel, do you have anything to add in terms of challenges? right now?
Certainly. I think that deploying quantum technologies in general is always challenging because they typically work well in the laboratory, and the
Yep.
gap to get them to perform well in real systems with real noise is large. As Frank said earlier, I think one of the major advancements that's happened in the last 5 years is that you start to see quantum networking technologies deployed on real fiber. Qunnect did this in New York, so we established a metro scale network, the first of its kind for distributing entanglement across New York City that was in an automated. So there's, I suppose, the challenges of this are, first, you have to be able to distribute it and maintain its fidelity, which is very difficult because entanglement is fragile by nature. But secondly, if you really want it to be a network, you need to also have the ability to automate its performance such that
Yep.
it's operating 24/7, weeks at a time. That's not the way experiments happen in laboratories, but that's the way networking happens in the real world. So
Yep.
Qunnect spent a lot of time thinking about how to make these real world instruments that support that type of information transfer in a 24/7 automated kind of way. And then we had great third party validation when our instrumentation was then used by Deutsche Telekom on the Berlin network to perform similar entanglement distribution as we had done on our metro scale network in New York. But what was more powerful about those demonstrations is that as a real telco provider, they were also broadcasting C-band traffic in the background. And I think that as we start to talk about scaling, this idea of initial adoption is necessarily going to be in hybrid scenarios because digital data traffic exists everywhere on fiber and is used for everything in our normal lives. So, how do you actually provide advantage and also broadcast simultaneously the quantum information in networks which have already been established? And I think that's one question which will always be there as quantum starts to scale. The other one that Frank alluded to earlier is this problem of distance limitations. When you're broadcasting single photons, single particles of light in order to communicate the encrypted information that you are trying to get from sender to receiver, the longer the fiber is, the more chance you have of losing that photon, and it starts to become distance limiting. In a normal digital network, you have repeaters, which will take those signals, clean them up, amplify them, and then repeat it. You can't do that in quantum without breaking the quantum itself. So therefore, in order to do this, you need to invent a new type of analogous technology called quantum repeaters. And Qunnect was first in the world to develop a quantum memory, which is one of the core components which are necessary for being able to enable quantum repeaters, because what they do is they introduce timing into the network. We commercialized our first generation memories in 2021, and since that time, we've evolved a second generation memory, which we have some publications out recently that hasn't gone to commercial market yet. But the challenges there are the more of these which you have in networks, you need to be able to actually interface them with all of the other quantum which technology which flows through the network itself. And those types of losses in the interfaces of all of these different types of quantum devices can become prohibitive at today's level of technology. So this is something that's still a technology gap that we and others are trying to fill. And stay tuned, because certainly that will be the next thing in our deployments.
Yeah. And then on top of that, once you get to the telco space, you want this to become multi-tenant as well.
Yes.
And that's another thing that is relatively difficult at the moment.
Let's talk some more about the real world use cases for quantum networking. Obviously, cybersecurity, secure communications is a big one. So I want to ask Frank first, what does being quantum safe mean to you? And what are some other practical applications we can expect to see first in this space?
Okay, so quantum safe for us, and I think that that's sort of the standard definition in the world right now, is that your communication is safe against the future threat of a quantum computer. Now, I think we've heard about Shor's algorithm, for example, and how easy potentially it would be for a quantum computer to break your current encryption, not only your VPN but also SSL, those type of things. Now, I think if you talk about this with experts, they all come up with different numbers, right? Maybe in 5 years, maybe in 10 years, somebody will say, well, maybe in 30 years. But right now, I think the point is you can no longer guarantee that the VPN connections or the encryption that you use today is going to be sufficient. So we are looking at ways to make sure that we can transfer data in such a way with such a version of encryption that it will not easily be broken. Now, there's two ways to go about. Basically, well, first of all, you need stronger encryption. That's one thing. And on the other side, for that encryption, you need something like a proper key and a proper key exchange. So the way we do that in the ring that I mentioned before in Paris is we combine PQC, so post-quantum cryptography, which uses stronger mathematical algorithms, but also the keys that we use for this system are being transferred via quantum key distribution. Now, the idea behind quantum key distribution, and I think Noel alluded to that slightly already, the whole point is that if you transfer a key, for example, or a qubit from A to B, and somebody in the middle is trying to capture your key, it basically means that on the other side, let's call it on the Bob side, Alice and Bob, we always refer to, on the Bob side, you will immediately recognize that somebody has been listening into your key exchange. So you could simply say, you know what, I'm not going to use that key anymore. We'll wait for the next key to combine or to come by. Now, if you do that, you would theoretically be able to guarantee a very secure connectivity from A to B. Now, that's what we're trying to achieve here right now. And right now, you see, we do this with a combination of those two technologies.
Noel, is there anything you'd like to chime in on real-world applications?
So I completely agree with Frank that I think the near-term applications of quantum networking are security-based.
Yes.
But what I would add is I think quantum key distribution is a very good first step, and the limitations that we've been talking about previously about distance limitations, etc., are real, and those will be overcome as technology continues to advance. But there's a second type of security application which quantum networking can enable, and that's this idea of how do you use quantum entanglement to protect the existing digital data traffic by turning the network into a sensor, or by doing types of quantum protocols which can't be achieved classically in order to do things like quantum position verification or authentication. So these are a new set of hybrid security protocols, where in one case, the qubits are broadcast in the background of existing digital data traffic. They themselves are not used for information, like in the case of a key, but they're used to turn the network into a sensor, where, again, they are very, very sensitive to any eavesdropper being on the line. So they become an eavesdropper detector, let's say. Another example, which has been becoming increasingly relevant and interesting, is the way that quantum can actually verify the position of the receiver between other two broadcasters in ways that classical can't do today, by allowing the one that you're trying to verify to perform a quantum test. So that is, again, analogous to the authentication methods that we use today, but a purely quantum protocol. I think both of those are quite powerful, but it's how quantum really augments existing digital network security. So it becomes, in that case, a physical overlay for cyber security that operates in the background of digital. I think the more forward-leaning applications, which we were alluding to in the earlier part of the podcast, are about how does quantum enable scale. So by broadcasting entanglement across these networks, you can now connect devices that use entanglement as a type of currency, and that's quantum computers, quantum sensors, and that allows you to start thinking about applications of long-distance distributed computing or the future quantum data centers, which are going to need to connect these things, as well as quantum sensor arrays. So I think that quantum networking will ultimately be the only way that we can achieve quantum computing at scale, the same way that we've started to see digital computing at scale. But it's definitely the next step, the forward-leaning vision.
So Noel, which industries do you think will benefit the most from these quantum applications that we've been talking about? Is it government agencies, financial firms? Who else stands to gain?
So McKinsey puts out a quantum technology monitor report every year, and they're predicting that quantum networking by the year 2035 is a $15 billion industry, which is significant. And that will drive the cost situation that Frank was talking about earlier. As the industry has more market demand, inevitably instrumentation and other things will reduce in cost so they can become a volume commodity. I think that the early adopters of almost all of these advanced technologies tend to be more on the governmental side, because if you're looking for customers that have extreme security needs, you're talking typically about finance, state and federal governments, power and utility grids, so anything in the critical infrastructure. And telecommunications providers like Orange and others service those niche customers for these ultra secure applications. So what you're going to see is a mix of defense driving the government side, which needs to, again, have secure communications for niche application. And then you'll have finance, critical infrastructure, et cetera, asking service providers in order to provide those types of networks for their usage.
Frank, how do your customers react when you talk about quantum networking with them? Are they excited or perhaps more cautious about the technology?
That varies from customer to customer, to be honest. Especially when we started working on the commercialization of quantum safe networks, we started talking to all our customers. We do a lot of presentations here and there, but we have customers that look at me and say, "I don't know what you're talking about. I don't see the issue." We have customers that tend to feel slightly scared. But I think one of the most important things to see is that a lot of our customers, when they look at this, they also look at how, as we discussed, how difficult or how complex it is to deploy all of this. And then you get to specific, like Noel mentioned, to specific customers in a niche, because they need to have a problem that's big enough to put all this effort in. That's right now. What we see as well is quite some customers that say, "Hey, but I'm very interested in this as soon as it gets to a level of technology that is achievable for me as an organization as well." So we have more and more conversations with our customers on how this would work for them. And I think one of the most important topics right now is not necessarily that everybody needs to jump on a quantum key distribution network, but I think the most important thing right now for most of our customers is to become aware of their current data estate. So what kind of data do they have? How is it transported? How is it stored? How is it secured? That type of stuff, I think, is the immediate call to action for most of the customers that we are working with, so that at least they have an idea that if the technology becomes within reach for them, what steps do they need to make in order to be quantum safe or remain quantum safe? So that's one of the things that we have most conversations about with our customers at the moment.
Noel, what do you think quantum technology needs to reach that chat GPT moment that we've seen for AI, or an application to show the world that quantum networking really works in practice?
It's a great question. I honestly think that we spoke about it a little bit earlier today. This idea of what people are referring to as Q Day, which is the day that quantum computers or computers in general, but most likely quantum computers, will be able to break our current encryption methods routinely, and that all of the mathematical algorithms that support our current encryption methods will no longer be sufficient. At that point, we have to have a different technology, which is going to be quantum resilient or quantum proof. And the first step towards that has been these PQC algorithms that Frank was mentioning that Orange is already implementing on their niche networks. These are quantum resilient algorithms that are harder to decrypt via the quantum computers of the future. But after that, you have to have a second layer of defense. And that means that you actually need to have quantum safe, quantum secure types of networking protocols that can protect from anyone being able to access a meeting or a transaction via the safe keys, and can also provide information about who's listening with these eavesdropper and other types of sensitivity type security methods. So I think where we are right now, well, the ChatGPT moment is going to unfortunately be hastened by the danger which is out there rather than just enabling. But I think that on the positive enabling side will be the moment that quantum networking tools start to show advantage in a broad way. You're going to see that customers, as Frank was talking about earlier, will start to trust that it's real. It's not just a demonstration. And I think that it's this point of constantly showing quantum advantage, which people overuse this term. But the advantage is clear. If it provides you more security than you're getting with traditional secure methods in today's digital networking, then it can be something that's implemented with advantage for the future.
Frank, what do you think a future quantum internet will look like? How long do you think it'll be before we see that become a reality?
So the way we look at it right now, I don't even think it's an official Orange business statement at the moment. But the way, at least I look at it right now, is that a quantum internet will be very much like the beginning of the internet. Of course, at Orange Business we have a big portion of internet in our hands, but for the near future, I expect those quantum networks to become, let's call it a network of networks. So we deal with it in, for example, in France or in the countries where we have local presence. And then somebody else will deal with it in their country. And then we interconnect those networks. But then we need those quantum repeaters, of course, to come by. Or we need to have something like quantum satellites, which are, well, they are on the radar here and there, but they're also not necessarily scheduled to become technically available anytime soon. There's a lot of developments ongoing with different suppliers, but somebody needs to start launching those satellites, and then we can start doing that. But I believe, personally, I believe that for now, we will do France and some other countries that we are local to, and then maybe the likes of I don't know, Deutsche Telekom will do Germany. That's something that we need to work on. And then it ties into your ChatGPT moment, because as soon as you start doing this, you get to a point where you have to have agreements between all those parties. And in reality, quantum technology is a difficult technology, but for all technologies, the agreements between all the different parties in different countries is usually even more time consuming than the technology itself. So I think that's also a call to action for the telcos to already get their act together, that as soon as Qunnect or Toshiba or anyone else has their quantum repeater stuff sorted, that we can just implement it and do not spend a lot of time talking to each other and fighting over commercial agreements.
And this question is for the both of you. What excites you the most about working in the quantum networking space?
Well, if I start, for me, to be perfectly honest, new technology innovation has excited me for the last, I think, 35 years, all the time. So for me, it's a new area. I've for Orange, I've been looking at all kinds of new technologies. But to be perfectly honest, I didn't study anything in quantum mechanics. So some of the concepts are really mind blowing for me, and that excites me a lot.
It's interesting. This is complementary to your statement. So one of the things that I think is most exciting about quantum technologies is seeing them actually come to the hands of normal users. So when quantum is actually empowering something where it's buried inside of the hardware, but it's completely software interface, but you know that the reason that it's working and providing all of these advantages is literally because quantum makes it work, but it's buried inside of a box where now it can be something that users across the world can start to implement.
So you're actually saying I shouldn't try to understand it, just use it.
Well, it should be the complement, right? It's at this point, there are things about modern compute and semiconductors and other things which you don't necessarily have to know the quantum physics for, but you reap the advantage on your smartphone,
Yeah.
right? And I think that's going to be an exciting moment with quantum networking as well. That right now the devices are sort of a first generation, similar to the digital internet, where they're supporting very early proof of concepts, and will hopefully drive down to what you were talking about a moment ago, which is the standards discussion. The moment that there are standards that are agreed upon by many countries worldwide, then you start to also see technology evolve towards miniaturization and being more widespread, and maturity in both hardware and software interfacing. All of that will come, but we're at the earliest days of trying to get it out there. And these proof of concepts on networks like Orange and Deutsche Telekom and others are important feedback for the designers of the future who will make these products.
Before we wrap things up, I'd like to ask you both, what's one thing that I didn't ask about that you think more people need to be thinking or talking about?
I think that people are always surprised that quantum networks are here today. So I think that we should acknowledge that metro scale networks like those created by Qunnect and, as we heard earlier, Toshiba, those that are being implemented by Orange and BT and other network providers, these are things which are here. So this is no longer a sort of theoretical, it might be able to be done. It's actually out there. So now that we acknowledge where the current state of the art is, I think the exciting conversations are about how that evolves and starts to become more widespread as a technology.
And on top of that, I think also people need to be aware that it's going faster than they think. I would even argue that this type of development goes maybe even faster than AI development have gone at the moment. So be aware that even, and I read that a lot in documents from analysts and so on, they say, well, these are the challenges, but be aware that most of the challenges for researchers are just things to overcome. And so if it's a challenge today, it doesn't mean that it's not going to work tomorrow. And I think that's something to keep a close eye on.
It's been great having you guys on the pod for such a robust discussion, and we cannot wait to see where this technology goes. So thank you both so much for your time, and to our listeners, we'll see you next time.